Assalamu alaikum everyone. Let us start our new topic called channel to coding. Our last lecture we discussed on source coding, right? Which was a small topic. This is actually our last topic in this semester, which is channel coding. So this is the first lecture in the channel coding. Let us draw a schematic diagram. Okay. So a communication schematic diagram. For example, we want to transmit a binary signal which is like 1001100 whatever. Okay, then it goes to a unknown block. We'll name this block later. Then this is the most simplest form of a schematic channel diagram, communication diagram. So this will be a channel. So this will be a channel. Channel can be wired or wireless, whatever. Then it goes to another block, and we receive the signal. Received signal. Received signal. Here the signal binary signal that we transmitted, we want to receive the same signal. This channel will actually add some like noise in the system. Means whatever message we want to transmit, this message may got corrupted in this channel. Means here the signal we received may not be the exact correct one. That's why for this correction we need, we name this block as a channel coding. Channel coding, and here it will be decoded. So the message signal which will be transmitted through a noisy channel, signal got or message got corrupted. So in that case, we in advance will add a channel code in the system so that the error message can be detected or corrected, so that we receive the correct message here. Okay, let us give you an example. If this is a transmitted message and this is a received message. Okay, so the transmitted message is, for example, 100110101, whatever. Then the received message is 100100101. Okay, you can clearly see that here the error occurred. This is the transmitted signal, same signal we supposed to receive, but we receive this signal. Means 1 bit error occurred here, that we actually express by our bit error rate. We have discussed about bit error rate in our multiplexing or different kind of modulation, right? ASK, FSK, PSK. Okay, this error happens in the channel, or we can say this happens due to the noisy channel. Now we need to correct the error which actually we receive, this one. For correction, what do we need? We need detect it. Okay, so we need to correct error or errors. Or in other way, we need to make the bit error rate as low as possible, like very low. Okay, but the question is how we can make this bit error rate or occurrence of the bit alteration that introduce the error as low as possible. How? Now see a simple example. So for example, we want to transmit 1 0 0 1 1, whatever this one. So what we will do, we will transmit, this is our transmitted bit, transmitter transmitted bit. Actually, sorry, this is actually our message bit, not a transmitter. This is our binary signal, this one, for example. So this is our binary. So this is our binary signal. Now we thought, okay, why not repeat the signal 3 times? So we, instead of transmitting 1, we will transmit 1 1 1. Instead of transmit 0, we will transmit 0 0 0. Same thing, 0 0 0. 1 we will transmit it as 1 1 1. 1 will be transmitted as 1 1 1. Means we will transmit the signal as like repeating in 3 times the same signal. Now imagine if one of the, for example, in the receiver, for example, in the receiver, one of the bit got corrupted. So 1 0 1 1 1 1. So 0 1 0. So 0 0 0. You see, this bit got altered here, right? And this bit got altered. So because we transmitted it 3 times, still if we receive it, we will receive it as a 1. If I receive it, I will receive it as a 0. If I receive it, I will receive it as a 0. I will receive it as a 1. I will receive it as a 1, which will be the same sequence of this one, isn't it? Okay, so what happened here? We actually repeated few times. So what we took a decision that, okay, we will repeat the signal 3 times, so that the majority, so we, what kind of decision we used here? What kind of decision? We actually make a majority decision rule, majority decision. In that rule, we say, okay, at least one got altered, yet we have still 2 corrected bits, right? At least one got altered or got corrupted, still we have the corrected bit. That's why based on this majority, we actually receive the corrected bit. We receive the corrected bit, or we receive the, or we reproduce the corrected bit. That's what we're trying to say. Okay, or reconstructed the receive bit. So our reconstructed bit sequence is nothing but actually is the transmitted bit sequence, which we transmitted, right? Transmitted bit sequence. So we actually we could recover the bit error. What we could do by this way, we could recover the error bit, error or altered bit by this way. So now we can how we do did this one, how we can correct it. So this is our observation from the previous example, that we could detect, and if we can detect, we can actually correct it, right? Detect and correct error bit by how? By adding redundancy. By adding redundancy. What is that? We actually repeated bit. One bit we actually repeated like 3 times. 1, 1, 1. We actually repeated 3 times. That's actually the redundancy. Now we give a definition. So the process the the process of the process of introducing systematic redundancy to enable detection and correction of error bit error bit over noisy channel is called, this process whatever we did so far is called channel coding, which is actually the title of today's topic, channel coding. Now the code that is used for this channel coding is called, so the code that is used for this channel coding is called error control code. It's called error control code. Error control code. So this way we introduce this to term or terminology, channel coding. This process by which we actually introduce a redundancy. By this introducing redundancy, we actually could detect and then correct error bit in the noisy channel. That is called channel coding, and the particular code is called error control code because it's control the error. Okay, now here we can see that 3 times we used a like our 1 bit message. This is our message bit is repeated 3 times. Then if it's 1 information bit, so if it's info bit divided by code bit, code bit, how many bit we used? We used 3 bit for this code, and what was 1 information was 1, isn't it? 1 information bit, this is the code bit, so 3, so 1 by 3, this is actually our rate of code or code rate of. So if there is redundant increases, our rate of code decreases definitely, because there is always a because the fundamental limit Shannon channel, because channel is restricted, so channel is not unlimited. So what we actually increasing? We increase the redundancy, you decrease the rate of code. So we can say increase redundancy, or we can say if we increase the redundancy, what will happen? This will actually decrease the rate, or rate of code rate will decrease, which actually ultimately will do what? If I keep increasing this value, what will happen? My rate will be keep decreasing. Ultimately, our system will be low efficient. So low efficient, isn't it? If our data rate decreases, the efficiency decreases, right? Or bandwidth decreases, whatever. Here efficiency, what in terms of what? In terms of its bandwidth. Now there is a another observation in this system. For example, our one we actually use three redundant bit. 1 1 1 means we actually repeat the three times. Now if 0 1 1, this is actually our receive. If we receive this one, then we can easily understand, okay, this bit got corrupted. But if somehow if we receive this also as a error bit, what will happen? Then majority dictates that the total bit will be 0. So we will actually decode it as a 0 bit. Instead of 1, we decoded 0. So means what? If 2 bit have means actually this in this example is 1 bit altered or 1 bit error happens, we can detect it and correct it. If 2 bit alters, we cannot detect it or correct it. Okay, means actually what? There is a limit. We will define this limit as a Hamming distance. Hamming distance. So in before we had one, like this is our corrected one. So we have this one, right? So one bit is different. So this Hamming distance dh was 1. Sorry, here for example, dh is Hamming distance is 1. But here in this case, what happened? 2 bit altered. Means actually Hamming distance is 2. This is how we calculate a Hamming distance. Number of, what is Hamming distance? Hamming distance dh is nothing but uh, number of number of number of dissimilar bits. Dissimilar bit are called the, like error bit. Number of error bit is called Hamming distance. Okay. So now we will, this is so far we give you an example. So now we will actually we will study a very traditional channel coding, which is called convolutional code. We call convolution code. This is actually our first channel code, like a classical channel code. Okay, or one type of channel coding, or error control code. Okay, so let us consider a bit sequence. Consider a bit sequence. What was our bit sequence in our example? We took, okay, this one, 100110001, whatever. I'm not writing 1001, this one sequence. I give it a name. Consider bit sequence is, for example, x0. Instead of writing 100, I'm just giving a notation: x0, x1, x2, okay, x2, blah blah blah. A bit sequence. Now, in convolution code, what will happen? That convolution 0 So convolution of like 0 bit C0 at time instant j. Okay, what we are trying to say, this is actually what? This is code bit, like code bit for 0, for example 0 at what time? At time j. That's why we write C0 j. Convolution code, that's why C convolution is nothing but xj plus xj minus 2. This is for what? This is for 0 bit 0, this is for 0. Okay, for bit 0. Okay, and for at time j. Okay, for example for code 1, of course at the same time j, if it's j, so this is for what? Code bit 1 at at time, of course j, at time j. Okay, what will be the code? The code is, conventional code is written as xj plus xj minus 1 plus xj minus 2. We are introducing you this convolution course. Actually, of course, it's a code. Actually, it's nothing but an algorithm will be there. So the programmer will write this program algorithm actually. Now here, this one, for example, these, they are what are those? Those are actually binary field arithmetic or arithmetic operation in binary. Okay, they are actually called binary field arithmetic. What is that? What is a binary field arithmetic? Okay, we will discuss it here. You see, in convolution code we generate code 0 and code 1, right? So we can say at so we can say at each time, means each j time uh, time instance, which is j actually in our cases, 2 code bit are generated. 2 code bit are generated, right? 1 and 0. So what will be the rate from our formula? Rate. What is that rate? Rate formula. Rate. Okay. What is the rate? So we can write the rate. Means actually the rate is what? We have 1 bit will generate by 2 code. So 1 by 2. Because we have 0 and we have 1. So there will be 2 code. So 1 by is half. Okay. Okay. Now binary field arithmetic. Okay. Let's see. Binary. What is that? Binary field, probably in your digital electronics, probably you already studied this binary field arithmetic. Let's see what it mean by binary field arithmetic. In binary field arithmetic, so what we will actually see two operation, like addition operation and product operation. So 0 plus 0 equal to, okay, so 0 plus 0 will be 0, 0 plus 1 will be 1, 1 plus 0 will be 1, and 1 plus 1 will be 0. Can you tell me what kind of operation is happening here? It's nothing but the XOR operation is happening here. Okay, and 0.0 and operation will be like this. Okay, we can write 1 and 0, 0 and 1 is 0, and 1 is 1 is 1. So this is actually an AND operation. Okay, from the above binary field arithmetic operation. Now, what kind of properties it have? Properties, properties. Pro this binary field arithmetic have properties called commutative operation. Commutative, commutative, mu, co- commutative. It also have associative. 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 What does it mean? It mean actually, for example, commutative means A plus B is nothing but B plus A, or A dot B is nothing but B dot A. Associative means A plus B plus C is nothing but A plus B plus C, or A dot B dot C is nothing but A dot B dot C. Like very common digital electronics stuff. Okay. Another one is distributive. It is also distributive. Distributive, which is nothing but A dot B plus C is AB plus AC, or A plus B dot C is AC plus BC. Okay, so we have seen. So if this is commutative, associative, and distributive, the question is now. Question is this convolution code linear? So the question is convolution code, is it a linear code? If yes, then operation is very easy. For that we assume. Okay, how to know that whether it's linear or not? Okay, let's imagine a bit sequence. For example, this one, like this. Bit sequence, like we consider a bit sequence x0, so consider 2 bit sequence now, so that we can see. So consider 2 bit sequence. 1 bit sequence is nothing but x0, x1, x2, blah blah blah, or y0, y1, y2, blah 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 blah. Okay, so what is the code bit 0 for x, for this series? What is the okay, code bit 0, okay. Now for coded bit 0, for sequence x, for sequence or info sequence, this is actually bit sequence. So for bit sequence x, Okay, c0, it was a 0, so give it a name x. At time instant j is nothing but xj plus xj minus 2. Okay, okay, so coded bit 0 for bit sequence x. For we will actually try to find coded bit 0 for bit sequence x. Let us write it other way, 2, so that I can write it 2 together. Okay, so for coded bit sequence, coded bit for uh, coded bits, coded, okay, for sequence, for sequence x, see sequence x, coded bit 0 will be here, and uh, coded bit 1 will be here. Okay, okay, then it's good. Okay, so x, c0, our x at time j will be nothing but x j plus x j minus 2. For 1, okay, we will, this is the same thing I'm writing here, eh? Which one? Yeah, this one. This is for 0, this is for 1. Okay, so xj minus 1, xj minus 2. So we'll write it again, c1, for x time instant j is nothing but xj plus x j minus 1 and j minus 2, right? Xj, x, what was that, x, j minus 1, j minus 2, xj minus 1, x j minus 1 plus x j minus 2. Okay, or we can write for sequence y, huh? So coded bit 0, huh? So we can write c 0 y j, huh? Equal to yj plus y j minus 2, and this is for coded bit 1, eh? So we can say c1 y j equals to nothing but y j plus x, sorry, y y j minus 1 plus y j minus 2. So we actually express for both x and y, for both 0 and 1. Okay, now, so what will happen, if we summarize, or if we can sum c0 x and c0 y is nothing but x j plus x j minus 2 plus yj plus y j minus 2 is nothing but xj plus yj. yj, because it's a by using our binary by our binary field arithmetic. This is an this is our commutative rules. Okay. 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 So, which is nothing but xj. Okay. Now one is remains here. One is remains here. X j minus 2 plus y j minus 2. So this is actually our commutative and associative both are actually applying here. So commutative and associative rules apply here, which is nothing but c of the x plus y if we apply that commutative rule. So this is what? This is actually nothing but what will happen? How we can interpret this one? We can interpret this is a coded bit 0. So this is a coded bit 0 for added information sequence. X and y is added now. So added x and y was individual bit sequence now because they are added. So it becomes added information bit sequence. Info bit sequence. Right? Yeah. Okay. So similarly we can write also that c0 xj plus c0, I'm writing it again, yj is nothing but c0 xy. That we find from our convolution code. What is actually is trying to say that coded or code followed by addition. This is actually code followed by addition addition, and this is actually addition of information bit, addition of info bit sequence followed by code Okay, so this is how we interpret our convolution code. Okay, so actually what we can see from here, you see, remember what was our fundamental question? Our fundamental question was if a convolution code, whether it's a linear, that was our where we put this question. Okay, so this was our question. This is our question. Is a convolution code linear? So this is actually solution of our convolution code. Now, does it look linear? This one, what it says? Definitely, it actually gives us a linear solution. That the code followed by addition is nothing but the addition of the bit sequence followed by code. So our what is our decision? Our decision or our conclusion is the code is linear. Our convolution code is linear. That's actually our conclusion about this convolution code. Okay, so here we will end up our discussion. In our next classes, we will discuss further of this convolution code. Thank you.